All right, welcome chemistry students. We are going to talk about in this chapter, chapter 10, states of matter. And if you remember early on, one of the early chapters in this course, we talked about matter. If you remember, we talked about homogeneous substances, heterogeneous, but we're going to dive in and focus a little bit more on the states of matter. Okay? And basically, this just means we're going to be looking at solids, liquids, and gases. The nice thing is you probably are really familiar with some of the characteristics of solids, liquids, and gases. We're going to be focusing on some of the traits of each of these, what makes them different, what are some of the things maybe that they have somewhat in common, and we're going to be looking at something called the kinetic molecular theory. Kinetic molecular theory, KMT, which kind of is the backbone for understanding the movement and the behavior, especially of gases. Okay? All right. I'll mention here, I said it's, especially of gases, it does illustrate also the movement of the molecules of particles of solids and liquids as well, okay? Not to neglect those. All right, let's talk first about this kinetic molecular theory, and I'll often write just KMT here, okay? Kinetic molecular theory. And so in your notes, you should have, this would be your section 10.1, you should write 10.1 in your notes, and heading here is the kinetic molecular theory of matter. And the first thing you should probably write down this definition, and you can put it in your own words. And I'll read it. Kinetic molecular theory is based on the idea that particles of matter are always in motion. Always in motion. That's amazing. Even though our eye doesn't detect it, particles are always in motion. Even if something seems to be solid and it is dense, something that we don't really pay attention to as the particles, thinking the particles are moving. We might think of particles moving when we think about steam, or we see water that's boiling, something like that. But even a solid material, those particles are always in motion. That's pretty amazing. As a result, when we think about this, the properties of solids, liquids, and gases are a result of the energy of those particles and the forces acting between them. This is key, ladies and gentlemen. If you understand this idea here, the rest of this chapter will just kind of fall into place. All right, so make sure you have that written down. Now, when we talk about gases and the kinetic molecular theory, we are going to assume, as we said, that the particles are in constant motion. Okay? So we're going to talk a little bit about gas particles here. So you have section 10.1, kinetic molecular theory, and you have the definition there. And the first thing we probably want to talk about here, let's talk about gases. Okay, so point A here, let's talk about gases. We're going to refer to gases as being ideal for right now. What we mean by that, an ideal gas, it is a theoretical gas. It's an idea, again, that the gas particles are in constant motion and also meet some other conditions. It's a theoretical gas, meaning we know that gases don't perfectly behave the way that we're going to describe, but we're going to use this description in order to better understand the behavior of gases in general. Okay, here are the 5 assumptions. Number 1, and I would suggest you write these down. Again, you can abbreviate it or you can put it in your own words, however you want to do it. All right. Number 1, gases consist of large number of tiny particles that are far apart relative to their size, meaning a gas particle is tiny, obviously, and it is far apart from another gas particle in relationship to the size of that particle. Now, the gas particles may be close together. All right, we would say, wow, those are pretty close together actually. But in comparison to the size of that particle, the distance between them is immense. Okay? Another way to say this is that when you have a gas, if you had, here's a bottle right here, and let's say there's some certain type of gas in that bottle, what we're saying when we say that the particles are far apart for gases is that most of this bottle is really just empty space. All right? Gases are going to expand to fill a container. We'll talk about that later. But most of this bottle here, if it's filled with a gas, is going to be just empty space because the gas particles are relatively far apart. Number 2, collisions between particles are going to be elastic. Collisions between the particles or even the container wall are going to be elastic. Here's what we mean by that. In an elastic collision, particles bounce off each other and they just continue to go on their way. They ricochet, they bounce off, they go different directions, but they never really connect or bond or hold on to each other, even momentarily. All right? A completely elastic collision means, as is described here, that there's no kinetic energy lost. In other words, they change directions, but they don't lose any energy. Okay? That's what we mean by a purely elastic collision. All right? So one particle may slam into another. It may transfer, this one maybe that's going faster, may transfer some of this energy to the other one, and now the second one's going faster and the first one's going slower, but no energy in general, no kinetic energy is lost. Okay? They go different directions, but and they may transfer energy. One may go faster or slower than before, but overall, the total collective kinetic energy is still the same as it was before the collision. All right? So no kinetic energy is lost. Number 3, gas particles are always in motion, as we mentioned, so they have kinetic energy. Okay? They can move freely in all directions. Kinetic energy, I'm just going to put a little extra here, and you can put this under number 3. Kinetic energy, please write this down under number 3. Kinetic energy is found by taking 1/2 times the mass times the velocity squared of that particle. That's kinetic energy. Okay? And I'm going to mention one other thing while we're talking about kinetic energy. Actually, I'll mention down here number 5. But kinetic energy is found, there's the formula for it, 1/2 times the mass times the velocity squared. Mass of that particle times the velocity of that particle, how fast that particle is moving. Okay? Number 4, there are no forces of attraction between particles. And this relates back to number 2. These collisions are elastic, which means they're not attracted to each other. They don't hold on to each other. Even for a split second, they just bounce off each other and then go different directions. Okay? No forces of attraction between the particles. So think of 2 types of balls that hit each other and they bounce off each other and just keep going in different directions. Or billiard balls. Bam, they hit each other and they just ricochet and they keep going in different directions. But they don't stick to each other even for a split second. Okay? Number 5, the temperature of a gas depends on the average kinetic energy of its particles. I mentioned up here that kinetic energy is 1/2 times the mass times the velocity squared. Well, that's what temperature is measuring. Okay? This is very important for you to understand. When you're measuring temperature, you are actually measuring the average kinetic energy of all the particles in the container. Does that mean that every particle has the same kinetic energy? No. Some are moving faster, some are moving slower. It's the average kinetic energy. The average. Okay? So when something is really hot, has a high temperature, why is that? Probably because those particles are moving very fast. It's the velocity that is increased. If it's the same particle as before, the mass hasn't changed if it's the same gas that you were measuring earlier. If the temperature is low, that means the particles have slowed down. They've lost kinetic energy and they've slowed down. Very important point. Okay? All right, as I mentioned, kinetic energy and temperature are related. Here's their formula for kinetic energy. If you didn't write it down before, please do now. Okay? Here's a quick thing that you should understand. If you have a mixture of gases, this is very important. I'm going to put a little star here next to it. If you have a mixture of gases, the particles of each gas have the same temperature. Okay, if I have a container here, it's a closed container, and in that container I have oxygen and I have hydrogen gas in that same container. And that container, the gases in that container, have a certain temperature. Well, all of the particles in there are at the same temperature. But that doesn't mean they're moving at the same speed. Why? Because the masses are going to be different. Oxygen is heavier than hydrogen. The mass of oxygen is greater than the mass of hydrogen. But if they're going to have the same kinetic energy, meaning being at the same temperature, their velocities must be different. So oxygen is heavy, so its mass is larger here, so it can move slower and have the same kinetic energy. Hydrogen is lighter, so it would be moving faster in order to have the same kinetic energy. Think of it this way. Think of it, let's think of a sport like football, American football. American football, two players collide. One tries to tackle the other, or they're blocking each other. If one player is very large and the other player is smaller, in order for them to collide and have equal force on each other, the smaller guy has to be running faster. Okay? Has to be running much faster. The big guy has much more mass, and as a result, if he's moving slower, he is going to be matching the kinetic energy of the smaller guy who's running faster. Or think of vehicles, a big truck and a small car. They collide. Well, who's going to win the collision? The only way the small car is going to win the collision is if it is going much faster. Okay? All right. So that's explained down here. If you want to read this paragraph, that is explained right there, talking about the hydrogen particles are moving much faster on average than the oxygen particles because they have less mass in order to be at the same temperature and have the same kinetic energy. Okay. So this kinetic molecular theory explains the constant motion of gas particles. Remember, the particles are always moving, even liquid and solid particles, as we'll see in a little bit. All right. Now, here are a few terms that we want to understand, and these should be in your notes, again, under the section of gases here. And these are, again, some physical properties that we're going to talk about when we discuss gases. Number one, expansion. Gases do not have a definite shape or volume. When you open a bottle of some gas, that gas is going to escape out of that bottle and fill up the room. Okay, it's going to keep expanding until it's bouncing off the walls of whatever container it's in. Okay, so these particles, because they have more energy, they move randomly until they fill a container. All right. Fluidity. What does that mean? Particles in a gas, we're going to assume again, these are ideal gases here. They don't have any attractive forces toward each other. So what do? They just pass by each other. They maybe bump into each other and then they ricochet off each other, or they pass by each other and they just keep on going. All right. So what we say that gases flow. Now you're familiar with liquids flowing, but gases flow as well. Gases are fluid states of matter that they can flow and move freely. The particles are not bonded to each other. They're not fixed to each other. Okay? They are fluid. So both gases and liquids are referred to as fluids. That's important for you to know because usually we only think of liquids as being fluid. A low density. If gases spread out, if they expand, remember what we said before? If you have a container of gas, most of that container is just empty space. The particles are so small, so it has a very low density. Density, by the way, please write this down. Density is found by taking the mass of all the particles, the mass of the substance, divided by the volume. Well, if you have a volume that is mostly empty space, this number, the volume, is going to be fairly large compared to the mass that is small. That's going to give you a low density. You're going to have very little mass, very few particles filling up a large space. Okay? Gases have low density. So gas particles typically occupy a volume 1,000 times greater than an equal number of particles in a liquid or gas or solid. Okay? Liquid or solid. Let's just remember they have a low density because the particles spread out. Lots of particles, few particles can fill even a large volume. Compressibility. Now, compressibility, as you might assume, when you compress something, you're going to squeeze it. Well, if gas particles are able to expand, then we could also put some pressure on them and force them to come closer together if we wanted to. So we could compress them. Compression, there's a picture here of a scuba diver, okay? And obviously that scuba diver is breathing air underwater. Well, how is he or she able to do that? You take a tank, a metal tank, and you force air into that tank under high pressure. So you're compressing the air particles to be really, really close together. So you can get a lot of air into a small metal cylindrical tank. Okay, and you can take that underwater and use it to breathe. So gases are compressible. You can compress them into forcing those particles to be closer together. Okay? It says here the volume of a gas can be dramatically decreased if you put pressure on them. Gases are often kept compressed in high pressure for different reasons. Okay? Next one, diffusion and effusion. These sometimes are confused, so you have to keep track of these and understand the difference. Diffuse basically means it is the mixing of the particles of two substances caused by their random motion. Remember, gas particles are always moving. So if you have here, this container has hydrogen gas in it, this container has nitrogen gas in it. Notice they're both diatomic, okay? And the two containers are connected, but this valve is closed. All right? If we open up this valve, then you'll notice that they start to mix because they're randomly moving. So there's going to be some hydrogen particles that are going to move this direction. There's going to be some nitrogen particles that move this direction. And they're just going to keep moving randomly until basically they're spread out evenly. Okay? That's the random motion of gas particles that's going to cause them to mix, diffuse. That's what we mean by diffuse. Now, effusion is that gas particles pass through a tiny opening. Well, that's what's happening here. They're passing through a tiny opening. Diffusion doesn't have to happen to pass through a tiny opening. Okay, it can happen in a large container. They don't have to pass through a tiny opening to diffuse. Diffuse just means they're going to randomly move and spread out. But effusion means that even a tiny opening, even this tiny opening here, gas particles can pass through there very easily because they're minute. They're infinitesimally small and can pass through very tiny openings. Okay? Now, how fast do they pass through an opening? The rate of effusion depends on the velocities of the particles. Obviously, if these particles are moving very fast, they're going to more quickly find this opening here and get through there. Okay? And what are the ones that are moving fastest? Those are the lighter ones. Remember we said that before? So low mass gases are going to effuse more rapidly, like hydrogen. So coming back here, this hydrogen here is lighter than nitrogen. These hydrogen particles, because they're moving much faster, these are moving slowly. The hydrogen is moving faster. They're going to eventually find that opening there and pass through there. So initially these hydrogens are going to be going through here much faster, and just a few nitrogens are going to find their way back. But eventually, over time, nitrogens will also pass through that opening. Okay. Now, I mentioned ideal gas. Ideal gas is there's no attraction between the particles. Okay? But that's not really what happens. Real gases, they don't behave perfectly according to the kinetic molecular theory. There is going to be, when real gases, when they come close to each other, there's going to be some attraction. It may not be enough attraction to hold them to each other. They may just kind of pass by each other, but it's going to affect their behavior a little bit. It might collide and maybe stick a little bit and lose some kinetic energy as a result of that, and then bounce off each other. Or as they're passing by each other, they might be attracted, and then it alters their direction of movement. Okay? So the point here is that ideal gases really do not exist. It's just a theory. We use that in order to simplify the characteristics of gases. Okay? A real gas basically is something that is in nature. It's the real gases that we come into contact with all the time. Okay? But it doesn't perfectly behave according to the KMT, the kinetic molecular theory. All right? Why is that? As I mentioned, real gases do feel some attractive forces between each other. They're minor, but if the temperature is really low or the pressure is high, maybe we'll talk about that later, the particles may have a little more attraction to each other. Okay? We'll talk about that when we talk about intermolecular forces. All right. So that pretty much concludes 10.1. We talked about the KMT and gases. KMT and gases. All right, let's look at 10.2. So you should have in your notes section 10.2, and we're going to focus on liquids. We're going to focus on liquids. All right. This is the first point that you need to write down. Intermolecular forces of liquids determine their properties. Now, let me just let you write that down, but then we're going to talk about what we mean by intermolecular forces. Okay? All right, let me just give you a quick example here. Intermolecular forces, inter means within the liquid. What is going to hold, let's just use water. What's going to attract one water molecule to another water molecule? Okay? So if we have a glass of water here, those water particles, they're not just randomly moving, or they're not expanding, they're not leaving the container here and just randomly moving wherever they want to. There's something that's holding them together. They're staying in that glass, they're filling up that glass and taking on the shape of that glass, and something's holding them together so that they're just not. Now there might be some water particles that are evaporating here, but for the most part the water particles are staying in the glass together. So there must be something that is holding one water particle to another water particle. That's what we mean by intermolecular, between molecules of the same kind. What's holding one water molecule to another water molecule? That's different than gases. Okay? When we had, hydrogen gas and hydrogen gas, they were not connected to each other. They were free. They were moving on their own direction in their own way. All right? But water molecules are attracted to each other, and they keep each other relatively close. So that's what we're going to talk about. Okay? Here are some characteristics you should know of a liquid. A liquid has definite volume. It has a definite volume, meaning you can measure the volume. Okay, you can say I have, a gallon of water, or if we use metric, I have cubic millimeter of water, or cubic centimeter. Definite volume, but it takes the shape of its container. You put water in a glass, it takes on that shape. You put water in a thin graduated cylinder, it takes on that shape because it's fluid. Okay? So that's the difference here. The difference between a liquid and a gas is, yes, the gas also took on the shape of the container, but the gas did not have a definite volume. A liquid has a definite volume. Okay? All right. Like a gas, liquid particles are constantly moving. Remember we said it's fluid. So you should write down that liquid is fluid. All right? But what are some differences? Well, some differences are that liquid particles are much closer together than gas particles. Okay? And we're going to talk about some intermolecular forces that hold these liquid particles closely together. I'll just mention a few of them right now. They're called dipole forces, London dispersion forces, and hydrogen bonding. Okay? We'll talk about those in just a second. I'll review those with you. We mentioned that liquid particles move freely. They don't just expand like a gas does, but they are fluid and they move freely. You can kind of think of them as kind of rolling and tumbling over each other. All right? But these intermolecular forces, these forces that kind of hold the water particles together, they're going to prevent that liquid particle from completely separating from the rest. So they are able to flow, but they don't completely separate. All right? So as we mentioned, liquid is fluid. It's a substance that can flow and take the shape of its container. Okay? Just a reminder, we said that both gases and liquids are fluids. The difference is that a gas expands to take on the shape of its container. Okay, it can fill the container completely, but a liquid has a definite volume. It takes on the shape of the container, but its volume is fixed, whereas a gas doesn't have a set volume and it doesn't have a set shape. Okay? How about density? Liquids have a relatively high density. What does that mean? It means that particles are pretty tight. They're pretty close together. Okay? Solids and liquids, we'll talk about solids in a little bit, have similar densities, although most substances are slightly less dense as liquids than solids. It just means that solids and liquids, the particles are packed pretty close together. Okay? And what about being compressed? Can liquids be compressed? Not a lot. No, hardly at all. Okay? Our gas particles, they're so spread out that you can put pressure on them and push them back closely together. But liquids and solids are already pretty close together. Those particles are already pretty tightly packed. And so even if you put a lot of pressure on them, you're not going to be able to compact them any more than they already are. Okay, so a relative incompressibility with liquids. Okay. How about diffusing? Remember, diffusing is the ability to mix because of the random motion. Well, liquids can diffuse as well. If you take water, here's a beaker of water, and you put another particle in there, another liquid particle. This is a dye. It has colors in it. Eventually, if you drop in some dye, here's some, let's say it's blue dye that is dropped into the water, that blue dye is not just going to stay congregated in one area. That blue dye is going to mix. It's going to keep moving, and as a result, it eventually will, you can see it's starting to spread out here in the middle picture, and eventually the whole water is going to take on a blue tint because it's diffusing. All the particles, because of their constant motion, random motion, all those water particles and all the dye particles are all going to mix eventually given enough time. Okay, that's diffusion. All right, here's an interesting characteristic of liquids. It's one that you have come across, but maybe haven't given it a lot of thought, but the idea of surface tension. This is kind of a neat thing about especially water, because those particles are experiencing intermolecular forces. Surface tension is a force that tends to pull adjacent parts of a liquid surface together. Now, that sounds complicated, but let me just explain what's happening here. Here's an illustration of some water particles. So each sphere is representing a water particle, okay? Well, those water particles are attracted to each other. They kind of keep each other relatively close. And as a result, what does that do? Well, there are attractions. This particle here is attracted to all the other particles around it, and the particles on the top are attracted to all the particles next to it and below it. And as a result, it kind of forms a little bit of a wall here on the surface. There's a little bit of a wall, and you can put some force on top of this water and not break through, because these water particles are attracted to each other. So the surface creates a little bit of some resistance. If you were to put an object that is light enough on top of the water, it might just sit there, okay? It might just sit there. So you've probably seen insects that are able to scurry across water because they're so light, and they are taking advantage of this surface tension. Or if you were to take, you might want to look this up on YouTube or try it yourself, figure out how you can float a paper clip, okay? Or a pin. I think maybe it'd be a pin. Pin might work better than a paper clip. A pin, a small pin, and you can figure out how to float a pin, which normally would not float on water, okay, because it's metal, it's more dense than water, but you could work it out where you could float a pin on water because of that surface tension. Look it up, and I'm sure there's lots of neat YouTube videos on that. Okay? All right. Another characteristic you need to understand of liquids is what's called capillary action. And it is the attraction of the surface of a liquid to the surface of a solid. Here's what I mean. All right? Right here, we have a piece of paper, or it's maybe a certain type of paper. It's called chromatography paper, okay? But this is paper for all intents and purposes, okay? And here we have some ink. We have some ink right there. And this piece of paper is put into a beaker, and down here you have a liquid. It might be water, or it might be some other type of liquid, but that is your liquid down there. Okay? This liquid is going to actually flow up. It's kind of odd. It's going to flow up the paper. Okay? It's going to flow up the paper, and as it does, it's going to pull this ink with it, and you get to see this ink kind of separate into the different colors, because these different colors have different polarities, which just means how kind of the particles might have large polarity or a small polarity, which means their electrons spend more time on one side of the molecule than the other. Okay, and so they are going to follow the water up this chromatography paper. Well, what causes the water to go up the paper? Well, the water molecules are going to be attracted to the paper molecules, and as they do, they pull other water molecules with them. And then they move up further because they're attracted to the higher paper molecules, and they pull more water molecules with them. So think of it as the water here is attracted to the paper, and as the water gets pulled up the paper, it's going to pull more of its water friends with it. And this is called capillary action. Okay? It's called capillary action. You can do this very simply. If you were to take a thin straw, all right? If you were to take a thin straw and put that into a drink or into water, a glass of water, you will see some of that water just automatically rise up the straw without doing anything. Okay? It might be a small amount, but the thinner the straw, the higher the water is going to go up the straw. Okay? And that's just because the water is attracted to the plastic in the straw, and as it is, it's going to pull more and more water up it until the attractive force between the water molecules in the plastic is equal to the force of gravity on that water, and then it won't be able to go up anymore. So that's capillary action. All right. Interestingly, capillary action is crucial to plant life because plants use that capillary action to transport water from the roots all the way up to the tallest branches and leaves of that tree. Okay. When you see capillary action, I mentioned the straw right here. I'm going to zoom in just a second for you. Okay, here's my straw. All right. When you look at capillary action, the water's being pulled up the straw, you're going to see this water have a little bit of a dip in it because the water particles on the side, I'll make it much bigger here actually. Okay. All right. The water particles on the sides here are attracted to the plastic in the straw, but the water particles in the middle are feeling more of the weight of the force of gravity. These are the ones that are being pulled up as well. But you're going to see a bit of a dip here in the water line. That's called a meniscus, just so you know. Okay, it's called a meniscus. You'll probably be asked about that. Okay, now water, liquids. I also often refer to water when we talk about liquids because it's the most common one for us. They can evaporate, boil, they can freeze, so we can change different phases here. So let's talk a little bit about this. So this is another point here that we want to get at. So this is another point in this section on liquids. Evaporation and boiling. Okay. Now, can we have a liquid change into a gas? Of course. Can we have a liquid change into a solid? Of course. All right. So a liquid can change the state, or sometimes we say phase. It can change to a solid or a liquid if the conditions are right, if the conditions change. All right? So what is vaporization? You must know that vaporization means when a liquid turns into a gas. Okay? Liquid turns into a gas. Any liquid has a potential of turning into a gas if the conditions are right. Okay? Well, in order to turn into a gas, it can evaporate or it can boil. Those are the two choices for a liquid to turn into a gas. In order for a liquid to vaporize, it can either evaporate or it can boil. All right? Now, evaporation is simply the process in which particles escape from the surface, but it's not boiling. The liquid's not boiling. If you took a glass of water, okay, you know that if you leave that sitting out for days and days and days, that level of water there is going to be less the next day and the next day and the next day because some of these particles have enough energy at the surface to leave their water friends and go into the atmosphere. Okay? It's evaporating. It's not boiling. It's not at the temperature to boil, but they do still evaporate. Okay? They will evaporate. So just know that vaporization can happen even if it's not boiling. Obviously, if it's boiling, it has reached the boiling point, and we'll talk about that in a little bit. Okay? Basically, these particles on the surface, they have enough energy, as I mentioned. Remember, not all these particles have the same kinetic energy. these particles have enough energy to pull away from their neighboring water friends and go into the atmosphere and become a gas. Okay? How about freezing? Well, freezing means you're going from a liquid to a solid. And in order to do that, you have to slow the particles down. Liquid particles are moving faster than solid particles. So if you want a liquid, the particles are moving pretty fast. Even though they're not escaping, they're not expanding like a gas, the particles are still moving, okay? If you want to turn that into a solid where the particles are no longer can flow and they're fixed in a place and just kind of vibrate, then you have to slow those particles down. And that you do that by removing heat. You take away their kinetic energy. Remember, temperature and kinetic energy are connected. You remove some heat, the temperature comes down, you're taking away their kinetic energy by removing heat. All right? When the average kinetic energy of the particles decreases, then those attractive forces pull them closer together, hold them tightly in an arranged fixed position, and all they can do is just kind of vibrate in place, just kind of oscillate and just kind of move. But they can't flow and turn and move very much. Okay, now you have a solid. Okay, so that's liquids. Guess what? That's right. 10.3, we're going to talk about solids. So let's look at solids here. And it starts off by saying, again, in your notes, 10.3, solids, and then make the different points through your notes so it's nice and organized. So, just to review, a gas does not have a definite volume. It's going to fill whatever container. It's going to keep expanding until the particles are filling the container, whatever container it's in, and it doesn't have a definite shape. It takes on the shape of its container. A liquid does have definite volume. All right, you can measure it. It doesn't keep expanding until it fills whatever container it's in. It just has a fixed volume. But it does not have a definite shape. It takes on the shape of the container. Whatever container you are putting it in, it takes on that shape. So a cylindrical, then it's going to be in a cylindrical shape. If you put it into something else that has a different shape, it's going to take on that shape because the particles flow. Now a solid, in this section, it has a definite volume, you can measure it, and it has a definite shape. If you take a wood block, it doesn't matter if you put it into a cup or a bowl or whatever, it's going to remain a wood block. It's going to keep that shape. Okay, we're going to talk about why that is as we look at the particles. All these characteristics relate to understanding the particles and the motion of the particles. That's why we started this whole chapter talking about the kinetic molecular theory, how particles move, or that they're constantly moving. So here's the first point. Point A, the particles in a solid hold fixed positions. They do not flow. They're not fluid like liquids and gases. They basically have an arrangement that they more or less stay put. Okay, that arrangement is fixed. Now they move, but they move within that arrangement. So we sometimes say that solid particles maybe vibrate or oscillate a little bit, but they don't have the ability to completely tumble, roll, flow, all of that. And that's because their energy level is lower relative to a liquid and gas of the same material. And so the intermolecular forces are holding them pretty pretty tightly together and in a fixed position. Okay? So right here it says, this is a key point, the intermolecular forces, remember those are the forces that are holding the particles together, have more influence over the motion of solid particles. Why? Because the solid particles don't have as much energy. Okay? They don't have as much energy. The kinetic energy is less than if they were a liquid or a gas. Important to note, remember I said solid particles are still moving, so they still have kinetic energy. They're still kind of moving, but the motion, as I mentioned, the motion of those solid particles is very restricted. It's very restricted to just vibrating in their fixed positions. Okay? They don't have enough energy just to go wherever they want to, or to flow, or to tumble. They're fixed right there, and the intermolecular forces are holding them pretty much tightly together, but they still have some energy, so they just kind of vibrate in place. Okay? Now, they form these different arrangements. They're fixed in place, and we'll talk about these different arrangements a little bit. Okay? There are two types of solids. There are crystals and what we call amorphous. All right? A crystal basically has a fixed arrangement, and it is an orderly arrangement. It's a repeating arrangement. It's a repeating pattern. They are arranged in a way that forms a crystal. All right? So, for example, let's see if we have an example here. Well, maybe we'll come to one later on. All right? A crystal has an orderly repeating pattern. So the particles are going to be arranged in a particular pattern, and that pattern repeats itself over and over and over again. Okay? Whereas amorphous simply means that the particles are just random. Okay? They're fixed together, they're tight, but there's going to be no particular pattern to how they are arranged. Okay? There's no particular pattern. Whereas this pattern here would probably repeat itself over and over and over. Okay? I'm just making something up. Okay, there's a repeating pattern. Here they're just all over the place. Kind of like they got just frozen wherever they're at. Okay? So amorphous solids are arranged randomly, very random. Just so you know, you should know that glass and plastic, those are two types of amorphous solids. Amorphous solids. They don't have a set arrangement. Lots of other solids are crystalline. So like salt crystals, we say, sugar crystals, those are crystalline. Okay? Just a quick comparison. Let's stop and just pause at this diagram here. You can see the difference in, if we zoom in into the molecular level, these are solids. They're arranged in a particular way. Okay? You can see they're fixed. And you have to imagine that there's layers of those, of course. Whereas liquid, they're attracted to each other, but they can flow, they can move, they can tumble. They're less fixed in place. And then gases, they're just moving all over the place. Very random motion. Okay? And again, why is that? If these are all the same substance, let's say these are all, let's say this metal here, let's say these are all sodium. Okay, this is sodium solid, sodium liquid, sodium gas. Let's just imagine that. If they're all the same substance, these particles, the energy for the gas is going to be very high, and so they have lots of motion. And the energy here for the solid is going to be lower. All right? These particles don't have enough energy to pull apart from each other. The intermolecular forces are holding them tightly, whereas gas particles have more energy, and they can really separate from each other and move apart. As we mentioned already, solids have a definite shape and a definite volume, okay, unlike liquids and gases. Well, liquids have a definite volume, but other than that, solids are different in that they have a definite shape, okay? And that's because those intermolecular forces are holding them in place. They're not letting them move, not letting those particles move, okay? Solids, when we go now from a solid, remember we talked earlier about changing phases, going from a liquid to a gas, liquid to a solid. Well, now, what if we go from a solid to a liquid? That is called melting. And every substance has a specific melting point. Every substance has a specific melting point. That's the temperature at which it begins to turn from a solid to a liquid. Okay? The way we do that is we are going to add heat. We're going to add energy, because you want those solid particles to gain more energy to start to pull away from each other and be more fluid in order to turn into a liquid, to break a little bit of that intermolecular force. Okay? Solids have high density. The particles are packed closely together. Remember, density is mass over volume. So in let's say, compared to a liquid, or let's compare it to a gas. Compared to a gas, the amount of particles for a solid in the same volume would be much, much greater. Okay? Your mass is much greater for a solid than a gas given the same volume. Okay? High density, the particles are packed closely together. Incompressible, like a liquid, you can't take a solid and put pressure on it and really change its volume very much. It's not going to happen because the particles are already packed closely together, so you're not going to make much of a difference. Okay, incompressible, you cannot compress it very much. All right, and solids have a very low rate of diffusion. Remember, diffusion is the mixing of particles. Very, 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 very low. It can happen, all right? So it says here that scientists have found that zinc plate and a copper plate, when you put a zinc plate and a copper plate and you kind of press them together, all right? This is the zinc, this is the copper, and you press them together, there is going to be a slow motion, slow movement of zinc particles and copper particles into the other plate. But it is so incredibly slow, okay? So slow. Very, very low rate of mixing, okay? Almost indetectable. All right. Now, this whole section here talks about different types of crystalline solids. I am not going to be asking you questions about the different types of crystalline solids, all right? All you need to know that is crystal is basically a specific arrangement. You can see this is a specific arrangement of particles here, sodium and chloride ions, in order to give it a repeating pattern. That's all you need to know about crystals. I'm not going to ask you about all of these different types of arrangements, possible patterns, okay? So you don't have to worry about those. Okay. And I'm just going to mention this briefly. I'm not going to hold you to too much of this as well. But basically in crystals, we already have talked about ionic bonds. All right? So that would be positive and negative ions that are arranged in a regular pattern. Ionic means you have charged particles. Okay? That is a strong binding force between ions. All right? Those solids are hard and brittle and have a high melting point because the ionic bond is very strong. You can also have crystals where they're sharing the valence electrons. That's covalent, remember? That's covalent. And you can also have metallic crystals. So that would be a metal, and those metal atoms are arranged in a particular way. Okay? But it's not crucial that you know these three or these different types as well. There's one more here talking about covalent molecular, but I'm not going to ask you about all these 4 different types. Just again, know that crystals have a particular arrangement. Okay? All right. I already talked about amorphous, meaning that it is basically a crystal that is just a random arrangement of particles. They're not in a set pattern. All right? This is just talking about the idea that we also sometimes call amorphous solids as supercooled liquids. They're kind of like they were liquids and then they lost their energy very quickly and the particles just kind of froze wherever they're at, very random arrangement. Because remember, liquids can roll and tumble, and then if you kind of make it lose its energy, cool it down very quickly, those particles are just going to stay fixed wherever they're at and are not going to have time to arrange themselves in a particular pattern. Okay, so sometimes those are called supercooled liquids. It's a substance that retains some properties of a liquid even at temperatures at which they appear to be a solid. So glass and plastic are mentioned as being amorphous or supercooled liquids because maybe over given enough time that glass or plastic can still flow and move, and the arrangement of the particles is very random. Okay? All right, that is 10.3. Took care of 10.3 there. Okay. This next section here, we're going to talk about, we talked about it a little bit, but we're going to dive into it a little bit more. And this is a key section, changes of state. So that just means that we are going to talk about a solid turning into a liquid, a solid turning straight into a gas, a liquid into a solid, a liquid into a gas into a liquid, or a gas into a solid. So each of the phases or states turning into the other two. Okay? You must know this. This is important. You have to know this. So you need to know that a solid turning into a liquid is called melting. There's an example. Solid turning into a gas, that's called sublimation. And that can happen. You can have dry ice, which is solid carbon dioxide. You've seen that, right? Solid carbon dioxide turning straight into carbon dioxide gas. Sometimes those are used like in shows, like to create the fog effect. All right. You have liquid turning straight into solid. Liquid, that's freezing, obviously. Liquid turning straight into a gas, we call that vaporization. We mentioned that. A gas turning into a liquid, that is condensation. And you would see that like if you took a cold drink and you set it outside on a warmer day, you'll start to see beads of water on the outside, and that's because the air in the atmosphere, sorry, the water in the atmosphere is touching the cold glass, loses its energy, and turns from a water vapor gas into water liquid, and it's going to condense. Gas to a solid, that is straight from a gas to a solid. That also does happen. That is deposition. Okay, so water vapor turning straight into ice, for example. All right. So a phase basically is any part of the system that has a uniform composition and properties. So phases are solid, liquid, and gas. Those are different phases. All right, solid, liquid, and gas. So a liquid or a gas or a solid, we say it's in a certain, that's the phase, or sometimes we say state. Okay. It's important to know, and we'll talk about equilibrium here in a whole nother chapter, but when something has reached its boiling point, melting point, freezing point, boiling point, what is happening is you have equilibrium, meaning that substance is going back and forth between two states at equal speeds. And we'll discuss that a little bit more. Okay, so hold on to that thought. Here we go. Let me give you an example here. Let's say that we have this flask has some water in it down here. Okay, and we have a cork on it, so it's a closed system, a closed container. All right. If we give this water some time, we know that some of these particles are going to have enough energy to leave the surface of that water and turn it into a gas. So there is going to be vaporization happening. Okay? So we have a number of these particles that are turned into a gas. You can see here we have water vapor. And down here we have liquid water. All right. Now this will continue. The evaporation will continue to happen until you have a lot of particles up here, and then some of these particles will be losing their energy and turning back into a liquid. Listen carefully. This is important because this concept we're going to see later on, and I want you to understand it now. So here we have water that's turning into gas, and gas vapor that's turning back into a liquid water. And they will continue to initially, listen carefully, initially the rate of vaporization is great and the rate of condensation is small. But over time, you're going to get more and more gas particles up here, and more of them are going to be losing energy and turning back into a water. And eventually, the number of particles that turn from a liquid to a gas are going to equal Do you hear that? They're going to equal the number of particles turning from a gas back to a liquid. So vaporization is going to equal the rate of condensation. Okay, I should actually put rate here. Rate of these two are actually going to be the same eventually. And once you reached equilibrium, you're not going to alter it unless you were to raise the temperature or change something. It's going to get to a point where the number of particles that are vaporizing are going to equal the number of particles that are condensing. Okay? And it takes a little time to get there because initially we had no gas, and then the number of particles that are going to vaporize is great, and the number of particles that condense is small, but over time the condensation rate increases in order to match the vaporization rate, and you're going to have both of them be the same, and that happens. When that happens, you have reached equilibrium. Listen carefully. Equilibrium does not mean you have the same number of gas particles as liquid particles. That's not what it means. Equilibrium is between the rate of vaporization and the rate of condensation. How many particles vaporize compared to how many particles condense. When the same number of particles that are vaporizing, that vaporize and condense, when those two numbers are the same, you have reached equilibrium. Okay? All right. And then we say that the pressure up here, the gas pressure that is created, the pressure by these gas particles create pressure because they're always moving and pushing against the container. When those gas particles, when we've reached equilibrium, the pressure exerted by those gas particles is our equilibrium vapor pressure. Vapor being the gas. Okay? Now this happens with liquids that are called volatile. Volatile means that they evaporate very easily. Okay? Again, this could be some type of liquid that's very volatile. It gives you an example here, such as ether or different types of alcohol, gasoline. You can smell gasoline very easily because it's very volatile. You open a bottle of perfume and you start to smell it in the room very quickly because it's very volatile. It evaporates very quickly. Okay? Well, those particles that are on the surface begin to vaporize, but when you get a whole bunch up there as a gas, they also lose their energy and they turn back into a liquid. But you're going to have here a certain pressure as a result of these gas particles. Those gas particles are going to create pressure there. And when you have reached equilibrium, you have reached what we call the equilibrium vapor pressure. Okay? The more volatile the liquid is, the higher this vapor pressure is going to be. Okay? All right. Another way that liquids turn into a gas, we talked about vaporization. They can just evaporate. They don't have to reach the boiling point, or they can reach the boiling point and begin to boil. And that's basically, it's the conversion of a liquid into a vapor within the liquid as well as its surface. So what's happening is, remember evaporation, it's these surface particles that are turning into a gas. Well, when you've reached boiling point, it's not just the surface particles. It is every particle in that liquid that has enough energy, and even the particle here or the particle there starts to turn into a gas. That's why it starts to bubble. Is you got a particle here, right here, that has enough energy to break away from its neighbors and turns into a gas. And so you start to see it boil or bubble. And that's because all the particles, not just the ones on the surface. Okay, before when we talked about evaporation, it was just those on the surface that had enough energy to escape. Now all the particles have enough energy to escape, and even the ones down here at the bottom, and they begin to turn into a gas and they begin to bubble out. Okay? That's boiling. Every liquid has its unique boiling point. You need to know that. Okay? So below the boiling point, only the particles at the surface have enough energy to go from liquid to gas. All right? As you increase the temperature, then that vapor pressure increases, and when equilibrium vapor pressure equals the atmospheric pressure. Let me just say that really quickly here, okay? Something begins to boil when the pressure pushing down on these particles. Imagine this stopper's not there anymore. This is from the atmosphere. When the atmospheric pressure pushing down on these particles equals the pressure of the particles pushing up from the evaporation. When those two are equal, it'll begin to boil. Okay? So that's kind of an important point there with boiling. Something is going to reach its boiling point when the vapor pressure of those gas particles equals the atmospheric pressure. Okay? All right. At the boiling point, this is important, the temperature of the liquid does not rise. Very, very important point. Okay, and we'll look at this later on when we look at a graph. But the temperature is not going to rise. Even though you still are pouring energy into it, even though you still have it over the flame, all that energy is put into breaking bonds. Breaking bonds. We'll talk about that. Okay? we're breaking those bonds and turning the liquid into a gas by allowing those liquid particles to break apart from their neighbors. Okay? I don't think I need to mention that. Okay? The amount of energy required to vaporize something, that is called the enthalpy. Enthalpy, you can just think of heat energy. You might want to write that down. Heat energy. Okay, the heat energy. And molar just means per mole. So what is the heat energy required to vaporize something, a mole of something? Okay, that is called the molar enthalpy of vaporization. The amount of energy, amount of heat energy needed to vaporize, turn it from a liquid to a gas, 1 mole of that particular liquid at its boiling point. That is called the molar enthalpy of vaporization. And you'll see that written as delta H. The delta here just means the change in heat energy. How much heat energy is needed to vaporize it. Okay? It's going to be different for every liquid because liquids have different forces holding them together. So the stronger the attractive forces between those liquid particles, the more energy it's going to require to vaporize that liquid. Okay? Alright, freezing is another important point. Freezing is when a substance loses energy and it's going to, particles are going to kind of snap into or be in a fixed position because they don't have enough energy to get away from each other. Alright? The freezing point, again, it's fixed. It's a temperature at which the solid and liquid are in equilibrium, meaning at freezing point you have particles that are turning into a solid, you have some particles turning into a liquid, it's at equilibrium, alright? Until you get below that freezing point, maybe it's going to be all solid then, or just above that freezing point, it'll be all liquid. But at freezing point, you have this equilibrium. You have a little bit of both, okay, a little bit of both. At the freezing point, the particles in the liquid and the solid have the same average kinetic energy. They're at the same temperature. Okay? So, freezing point, the amount of energy you take out to freeze something, let me just say this here, the energy that is released during freezing must have been energy stored in the liquid. Remember, we put energy into it to melt it, or we can take energy out of it to freeze it. Okay? Melting is the reverse process of freezing. So we freeze something, it goes from a liquid to a solid. You melt something, it goes from a solid to a liquid. And the energy flow is opposite. In order to freeze something, you have to take energy out of it. Heat energy has to come out of that substance. In order to melt something, you got to put energy into that substance. Just think about the particle movement. If you want something to go from liquid, where the particles are flowing and tumbling, have more energy, to a solid where they're fixed, you got to take away that energy so they stop moving so much. If you want them to go from a solid to a liquid, you got to put energy into them so that they go from their fixed position and they're able to have more energy and pull away from their neighbors a little bit more and start to flow and roll and tumble. Okay? So that's what this is showing here, is that If you have a solid and you add energy, it can potentially turn into a liquid. Okay? And just like we talked about the molar enthalpy of vaporization, well, we can talk about the molar enthalpy of fusion. Fusion means the amount of energy required to melt 1 mole of a solid. Okay, to melting, we talk about fusion. And then one other thing, these are less common, but you should know sublimation and deposition. It kind of, sublimation and deposition kind of skip over a phase. All right, so a solid can go right into a gas if given enough energy, or a gas can go right into a solid if enough energy is taken away. Okay, so sublimation is when you go from a solid directly to a gas, and deposition is when you go from a gas directly to a solid. All right, this diagram is very helpful. This kind of sums it up all up for you and shows you the different names of the phase changes. So this is something that you should know, and you can refer to this anytime you take a test or a quiz. Okay? Okay, let's spend a little time talking about what a phase diagram is. Remember, phase, we're just talking about solid, liquid, or gas. And we're going to look at specifically for water. Okay? You'll notice that this chart shows pressure, and ATM is a unit for pressure. It's an atmosphere. So pressure over here on the y-axis, temperature in Celsius on the x-axis. Okay? Basically, you know that as the temperature increases, if the temperature gets higher and higher and higher, that you're going to be able to turn a solid into a liquid into a gas. Okay, so watch what happens here. If we're at a low temperature, if I move from left to right across this graph, you'll notice that we will go from this region, which is the solid region. We go from left to right, go from solid, then we turn into a liquid, which makes sense as you raise the temperature. You're going to be able to go from a solid to a liquid, and then eventually if it gets really high, the temperature gets really high, you'll turn into a gas, which is the vapor here. So we have 3 particular regions: solid, liquid, and gas. And you'll notice that when you move, for the most part, from left to right, you're going from solid to liquid to gas, those different regions. Let's look at pressure. Pressure, well, if you put a lot of pressure on something, if the pressure gets really high, this is where pressure is getting higher this way, okay? If the pressure is really high, high pressure means you're going to condense it. You're going to push those particles close together. That's a solid. That's getting closer to a solid. If you take particles and you push them close together because of the high pressure, you're going to have, more likely, the particles are going to be dense, and it's going to be more like a solid than anything else. So let's go up here, okay? So you'll notice that when we go high pressure, you're going to go from a gas region into a liquid region because you're going to push them closely together. Or you might go from a gas region straight into a solid region. But the idea here is that gases are have a low density. Solids and liquids have a high density. So if you push them, high pressure means you're going to turn a gas into a liquid or gas into a solid. Okay? So this diagram is showing you a particular temperature and a particular pressure. Is it going to be a solid, liquid, or gas? That's what it's telling you. Okay? So if you pick a particular temperature, if I say, let's say it's about 50 degrees Celsius and a pressure of 1 atmosphere, and I follow 50 degrees Celsius and 1 atmosphere, and I find where those 2 values intersect, and I am in the liquid region, I know that I have a liquid. I have liquid water at 50 degrees Celsius and a pressure of 1 atmosphere. Okay? That's how you can determine what state you're in given the temperature and the pressure for any substance. Every substance has its own unique phase diagram. Okay? Now, there are a couple of regions here that I want you to understand. If you have a temperature like 100 degrees Celsius and a pressure 1 atmosphere, and they intersect, those values intersect, and put a point right on one of the borders, one on the border line here, that means that you are in equilibrium. You are at an equilibrium point here. Remember we talked about equilibrium. And in this case, it's equilibrium between liquid and gas. Basically, this is a boiling. It's boiling here, okay? Equilibrium point between the two phases that that line is dividing, okay? The two regions. So if I look here, if I pick a temperature here, okay? This temperature is 0 at 1 atmosphere. Well, that's the freezing point of water, and you'll notice it's on the border between liquid and solid. So this is the freezing point, and it's in equilibrium between liquid and solid. It's right in between the two. You have a little bit of both in the rates of freezing and melting are the same. Okay? What about if we had a place where all three borders come together? That's called the triple point. And that is the temperature and the pressure in which you have all three phase changes happening at the same time and in equilibrium. At this particular temperature and pressure, you have some liquid, some gas, and some solid, and all three rates are the same, and that is called the triple point. Okay? Because that's the boundary between all three different regions. All right? And then there's one other value that I want to mention here, and that is up here. And this point right here, this is where basically you're at the end of the boundary line between liquid and gas, and that is at a very high temperature, and a very high pressure as well. So if something's at a very high pressure, or sorry, high temperature, if something's at a very high temperature, it's most likely a gas. But if you also put it under high pressure, you're pushing those particles close together, well, that's more likely to be like a liquid. So here at this critical point, it's not really distinguishable to say what you have. Do you have a gas or liquid? It's going to have the behavior of both. Being at a high temperature, those gases, those particles are going to be very randomly moving, but under a high pressure, they're going to be quite dense. They're going to be pushed together like a liquid. So as a result, this critical point here is the point where you kind of lose the boundary between gases and liquids. All right? So this is the phase diagram, and every substance has its own phase diagram. All right? I mentioned the triple point. You need to understand that. I mentioned the critical temperature and the critical pressure, and which reaches the critical point where kind of the boundary between liquid and gases disappears. Okay, so you need to know those different important points, as well as be able to interpret the graph like this. And I'll probably give you some more information in another video that might help you. Okay. All right. In our last section, we're going to talk a little bit more specifically about water. And that's just because water, being a liquid, we're talking about states of matter, water is so important to us. Okay, we need to understand water a little bit more and some of the characteristics here. Okay? All right. First of all, we have seen the structure of water before. We've seen the structure of water when we talked about molecular geometry. We know it's a bent shape. It has one oxygen atom and two hydrogen atoms, and it has some lone pairs of electrons up here in its diagram, and it pushes those bonds between the oxygen and hydrogen down a little bit, giving it this bent shape. Okay? Well, that bent shape gives water some really unique properties that make it very helpful to us. If this molecule is not symmetrical, the electrons are going to be spending more time at one end of the molecule than the other end of the molecule. Remember, we call that being polar, polarity. So polarity just means that oxygen is going to be pulling the electrons. It's more electronegative. It's going to be pulling the electrons to its side a little bit more. and the hydrogen are going to lose those electrons, and so they're going to become a little more positively charged. So this whole water molecule has a negative tendency on the oxygen side, and it has a positive tendency over here on the hydrogen side. It is polar. Okay? Being polar gives it a bit of a one-sided charge. The overall molecule is neutral. Okay, you have the same number of protons and electrons, but electrons spend more time over here on the oxygen side than they do on the hydrogen side, and so it is imbalanced. It's imbalanced, and the one side of the molecule is a little more negative than the other side, and that makes water polar. Okay? If it's polar, then it's going to be attracted to another water molecule in this manner. So the negative side of the water is going to be attracted to the positive side of another water. And this negative side is going to be attracted to the positive side of another water. That is the intermolecular force that holds water molecules together. This positive side of the water is going to be attracted to the negative side of another water. And so these intermolecular forces are what holds water together. And it's a fairly strong intermolecular force, as intermolecular forces go. So water has a pretty strong connection to each other. Okay? We call this type of intermolecular bonding or intermolecular force hydrogen bonding because it involves hydrogen. Okay? And it's one of the stronger intermolecular forces. All right? That intermolecular force is going to have to be overcome in order for water to escape the liquid phase and turn into a gas. Okay? Water, the density of water, it is, again, being a liquid, it's pretty packed together. And if you were to freeze water, take heat out of it, it's going to form a crystal with a set arrangement. Okay? Now there is one characteristic of water that is very unique, and that is that as a solid, this is important, as a solid, it is less dense than as a liquid. That's pretty unique. That's not what we would expect. We usually think solids sink, right? Sorry, my pen is not working very well here. Okay? But in this case, the solid is less dense than the liquid. So the density of water actually decreases when it freezes. That's interesting. The solid of water, ice, is less dense than liquid. That is unique for water. That is a pretty unique property, and it's incredibly important for life on our planet because this unusual property helps protect organisms that live in water. If lakes froze from the bottom up, it would kill all of the plant life in that lake or pond or river, okay? But they don't. Lakes freeze from the bottom down, and eventually they can't, the whole lake won't freeze because the under the ice there, it's going to be too warm. It's going to kind of be insulated, all right? So most liquids freeze from the bottom up, but not water. Water freezes from the top down because the solid begins to float. The water, when it freezes, it goes to the top. Okay? And then the surface water is cooler than the deeper water, and the ice stays on the surface of the lake or pond because it's less dense, and it acts as an insulator. And that keeps the plant life and the lake or pond life from dying. Okay? That's amazing. All right? The density of water is pretty close to 1. The units are 1 gram per cubic centimeter. Okay? And you'll notice here it says the density of liquid water is close to 1. The density of solid water is less than that. So that's why it floats. And that's because it kind of expands when it freezes. It's a unique property of water. Okay? Water has a pretty high boiling point, relatively high, higher than some substances. And it can absorb a large amount of kinetic energy before it begins to boil. Okay? That's another pretty wonderful trait. And we use that trait for water all the time. So, for example, in your car, to keep the engine from overheating, there's a radiator. And that radiator forces water around the engine to pull heat away from that engine. And then the water cools down and it's circulated around the engine again. That water can absorb a lot of heat away from the engine. Water, because of its intermolecular forces, can absorb a lot of heat before it begins to boil or begins to get too hot. Okay? It has a very high, relatively high, a high molar enthalpy of vaporization. Remember, that's the amount of energy required to turn it into a gas from a liquid. That's fairly high for substances. Okay? All right, let's go through a sample problem here. It says how much energy is absorbed when 47 grams of ice melt at a temperature of 0 degrees and a pressure of 1 atmosphere. So how much energy is absorbed? So you're going to be given some values to help you with this. You're given the mass of water, and you're going to be given the molar enthalpy of fusion. Now don't worry about this too much if you don't understand it. Just look at the units. kJ, that stands for kilojoules. And this is your unit for energy. This is energy. So your answer should be in kilojoules, or maybe just joules at the end. Notice what it says here, per mole. This is per mole. Well, you're not given moles. You're given mass. But we can convert from mass to moles, right? Yeah, we've done that before. So here's all you're going to do. You've got to take your 47 grams of water and convert it to moles. How do we do that? We divide by its molar mass. Water, we look on the periodic table, oxygen is 16, each hydrogen is 1, so that's 2. 2 plus 16 gives us 18 grams per mole, straight from the periodic table. 18 grams, so I take my 47 grams. I've got more than 18. Okay, 47 divided by 18 gives me 2.61. So I have 2.61 moles of water. That's what my 47 grams of water is. So what does that mean? Well, in order to fuse, in order to fuse the water here, I need 6.009 kilojoules per mole. So all I do is I look at my units here. I want to cancel moles of water and convert to energy. So I'm going to multiply by 6.009 kilojoules per mole of water. The moles of water cancel, and I'm basically taking my 2.61 moles and multiplying by the amount of energy per mole. I don't just have 1 mole. I've got 2.61, so it's going to be 2.61 times the 6.009. And this is how much energy it's going to take in order to, it says here, a mass of 47 grams, which was our 2.61 moles, all right? And we're going to require 15.7 kilojoules is going to be the amount of energy absorbed in order to melt that ice, that 47 grams of ice. Okay? Fusion is melting. Here again, what mass of steam is required to release this much energy? This time, you have the energy and you want to find out how much steam, the mass of that steam that was condensed. Okay? Okay, So what you're going to do this time is you're going to start with energy, and you're going to use our well, they don't mention it here, but they would have to give you right here. This is given to you, would be given to you. This is the vaporization enthalpy, the enthalpy of vaporization for water. So this is the energy that we know is being taken out of the steam, and we know that 40.79 kilojoules of water, 40.79 kilojoules are taken out per mole of water to help it condense. It's also the amount that would be put in to turn it into a gas. So both directions, either taken out or put in. But in this case, we're taking it out. We're going to try to release that energy. So this is the energy that's released, and we know that 40.79 kilojoules is released per mole of water. Well, we released a lot more than just 40.79. Look at how much we released. It's 4.97 times 10 to the fifth. That's a lot bigger than 40.79. So we must have been using more than just 1 mole. Okay? So you would take this number, 4.97 times 10 to the fifth divided by 40.79. That'll give you this value. And then you take that value, that's how many moles you have. See our units here, moles, and then you would multiply by the molar mass of water to find out your mass down here. This would be the mass in grams. Okay? And I know you can do those calculations. All right. That basically wraps up Chapter 10, and I'll make another video that goes over the Chapter 10 review questions. Okay? All right, keep up the great work. Let me know if you have questions, okay?